Hi students, in this chapter we are going to learn about linear momentum and collisions. What exactly is this linear momentum? You must have learnt in lower classes that it is the product of the mass and velocity of a body. But why is it relevant? Also, if a collision like this occurs, then how are the velocities redistributed after a collision? And how is it so that the bodies are deformed after some collisions but not deformed after other collisions? We learn about all of these things in this chapter related to the conservation of linear momentum and collisions. So, what is linear momentum in the first place? The product of the mass and velocity of a particle is defined as its linear momentum. It basically reflects the impact a body has on another body when it collides with it. It is a property to represent completely the motion of a body. The velocity of a body multiplied by the mass of the body basically tells us about the impact factor about the body, how powerful the body is. That's what linear momentum tells us. Take a look at this car. What is the impact of this car? Take a look at this bus. What is the impact of this bus? How powerful is the bus? How powerful is the motion of the bus? That's what momentum represents. If the car and this bus collide, whose impact is more? Clearly, the impact of the bus. That is what momentum represents. There you go. Linear momentum is mass into velocity. Linear momentum is a vector quantity, as velocity is a vector quantity. It is represented by the symbol P. P equal to mv. So, if the mass of this car is 100 kg and it's moving with a velocity of 30 meters per second, in that case, the linear momentum of the car is 100 into 30. That is 3000 kg meter per second. There you go. Just like we can, calculate the linear momentum of a particle by multiplying its mass by its velocity, we can calculate the linear momentum of a system of particles also. The linear momentum of a system of particles, that is, say the linear momentum of these three particles combined, is the sum of the individual linear momentum of each particle. Understood? So the net linear momentum vector of a system consisting of these three orange particles is m1 v1 vector plus m2 v2 vector plus m3 v3 vector. So basically the linear momentum vector of a system is the summation of m into v vector for each of the particles. Now we can derive one fascinating fact from this conclusion. You see, RCM, or the center of mass vector of any system of particles, is clearly sigma mr divided by sigma m, isn't it? After all, the center of mass vector r is m1 r1 plus m2 r2 plus m3 r3 divided by m1 plus m2 plus m3 and so on, isn't it? Therefore, differentiating this expression, we get VCM equal to sigma mv divided by sigma m. But sigma mv is basically the linear momentum of the system, isn't it? That's what we just wrote here. We said pieces equal to sigma mv. Therefore, we can replace sigma mv vector by pieces, that is the linear momentum of the system. When we do that, this is what we get. Linear momentum of the system equal to velocity of center of mass into sigma m. So the linear momentum of the system is the net mass of the system into the velocity of the center of mass of the system. Understood? So the linear momentum of these three particles is equal to the velocity of the center of mass of these particles into the sum of the masses of these particles. Understood? So this is one important formula that you have to remember. There's yet another fascinating conclusion that we can draw. If you consider any system and if no force is acting on the system, in that case, we already know that the velocity of the center of mass is constant. Now, linear momentum will also be constant in that case. That is because the net linear momentum of the system is velocity of center of mass into sum of masses, isn't it? Since the velocity of center of mass is constant when no forces are acting on the system, therefore the linear momentum of the system is also constant when no forces are acting on the system. So if there is any system and there are no external forces acting on the system, in that case the linear momentum of the system will be constant. This special statement, linear momentum is constant when no force acts on the system, is called the law of conservation of linear momentum. This means that initial momentum equal to final momentum equal to momentum at any instant, because there's no force acting on the system and so the momentum will not change. Let us see what is happening in the question in the first place. Well, there is a man at the origin and he is moving along the y-axis upwards with a velocity v1. Then there is this mass m which is rotating around in this circle of radius r. The speed of the mass m is v2.